Hello, you absolute legends. This is a fairly long video that's going to be about chemical equilibrium. In particular, I want to hit this point about how to use a Rice table. Just very simply, chemical equilibrium, when to use a Rice table. If you need to know the value of capital K, or if you want to know the molarities of reactants and products at equilibrium. Those are two instances you would be using a Rice table. We're going to be using a Rice table to calculate capital K right now. Now with this example right here, I'm going to walk through using what we have done in one of our labs. In this spectroscopy lab, this is the balanced chemical reaction. And I have this product written as a bright red because if you recall, the solutions were bright red because of the formation of this compound. I want to just draw out an atomic vision of what is going to happen in this reaction over time. Initially, remember, we want to know the concentrations at equilibrium so that way we can calculate capital K. That's what we're trying to find out here. Initially, you mix your solutions and there are some molarities of iron and there are some molarities of thiocyanate present, and you know these molarities because you set them up. And this is the initial. Now, very quickly, now this initial status of atomic vision only happens for like a millionth of a second, because as you know, and as you've observed very quickly, that there is a change and then equilibrium is observed, and at equilibrium you will have some of this compound produced. So I'm just using red dots to kind of make that up, to represent that there. But we also know at equilibrium that at chemical equilibrium, it is a dynamic environment and there are reactants and products, there are still reactants present, just in a smaller concentration than they initially started with. So there's still going to be some Fe plus 3 remaining, some unreacted reactant, and also some unreacted reactant present. We have the initial, the equilibrium, and there is going to be a change that occurs. And this is atomic fission pictures right here. The Rice table is meant to really organize our thoughts and to make sure that we organize and keep tabs about where we're starting, what's changing, and what's happening at equilibrium. And now here we see all of our letters of the Rice table. The reaction, the initial molarities or concentrations, the change, and the equilibrium, the molarities at equilibrium. Sometimes this is referred to as an ice table, but the real powerful part of this is that you can keep things organized. So please have your Rice table set up. The only thing that goes in here are going to be units in molarity, moles per liters. So I recommend you don't write capital M, write in moles per liters, making sure everything's set up here. In your lab, the initial molarities of your reactants is something you know because you designed these 4 solutions in Part B. For each of those solutions in Part B, you have to do a Rice table for each of those solutions. For the first solution for Part B, the concentrations were, you calculated this up right here using the dilutions and stuff. I am just going to make up some numbers. This was 0.002 moles per liter. And this right here was 0.002 moles per liter. Again, I'm just making up numbers that may or may not match up what was in your solutions for right here. Now, initially, these things are at their highest concentration they're ever going to be, and the product is at 0 concentration because in this first millisecond of the reaction, no product has been formed. The change. The change is just a very logical step, just very logical. If when a reaction starts, the reactants will go down in concentration and the products will go up in concentration. Just a very reasonable thing. If you start only with your reactants at the highest possibles, then they are only going to go down an amount. And they are going to go down an amount that's proportional with proportional in the balanced chemical reaction. So in our this balanced chemical reaction is all 1-1-1. So this is going to go down 1x. I don't know how much it's going to go down, but it's going to go down an amount with respect to the balanced chemical reaction. This reactant is also going to go down with respect to the balanced chemical reaction some amount. The product is going to go up with respect to the balanced chemical reaction some amount. So each of these symbols here represents a logical aspect. The negative sign is meant to describe what direction the concentration is going to change, whether it's a reactant or a product. This number here is the same type of cofactor from the balanced chemical reaction. I didn't make this one up. It came from the balanced chemical reaction. And the X is how much. Okay, this is a number that you have going to measure or evaluate. So this is the crucial line here, the change. So at equilibrium, because we have everything organized nice and vertically, keeping everything under its spot in the reaction, in this final line here for equilibrium, we type in, the change at equilibrium, it's going to be whatever our starting concentration was minus 1x. Like that is going to be our answer for the equilibrium. For this other reactant, I'm putting parentheses around these just so they don't get too messy, too close together here. Minus 1x. Okay. Now our product here went 0 plus 1x. Now here we have things where each of these can be plugged in to our capital K expression, but we have an unknown x. So how can we solve for an equation that has two unknowns? We can determine what x is. With this part, in part B, you have developed a calibration curve at 450 nanometers for this particular cation. That is that iron thiocyanate. So you know it started at 0, and you know it went up a proportion that you derived from your calibration curve. You measured the absorbance. So this x value here is what you get from your calibration curve. For this right here, I'm just gonna take a number. Here is a calibration curve of somebody else in the course. Trying to get this in focus here. This is absorbance. This is absorbance on the Y and molarity of iron thiocyanate in the X. And I'm looking at this top graph right here. Short of looking at these numbers right here, if we measure the absorbance from the solution and then fit it into the Y equals mx plus b, we should be able to calculate the concentration of iron thiocyanate. So let's imagine, I'm just going to make up a number in here that we measured this absorbance to be such a value, and we figured out that X from the calibration curve represented and this is what you would read off of the calibration curve after solving for the y equals mx plus b Beer's law plot. I just made this number up, but you would use your y equals mx plus b here. Now that we have a value for x, we can plug it in everywhere we see x and evaluate these numbers here. So 0.00012 moles per liter, that is how much this went up, the product. Logically, that means the reactants must have went down the same amount. So we would put in the 0, what was that, 4 zeros? 1, 2. Really jamming it in there, but I hope you can follow what's going on here. So now this is a solvable problem. 0.002 minus 0.000012. That's going to be a real number. This is also going to be a real number. This is also a real number. If we have all, this is how we set up our Rice table. We have our reaction. We use a Rice table when we're asked to calculate capital K, and we need to know the concentrations at equilibrium. We start out with our reaction on top. The initial concentrations of our reactants or products are usually given to us in the lab that has been designed. The changes, this is probably the most confusing row, because each of these three terms is just a logical step. The reactants go down because they're starting as high as they can. We're starting with 0 products, so the products would go up. These numbers are going to change depending on what the balanced chemical reaction is. If your balanced chemical reaction had 2 3s and 4s, there should be 2 3s and 4s down here. And the X is what we're ultimately solving for. In this example, we're solving for X spectroscopically using a calibration curve at the 450 nanometers. Once we have all of these numbers plugged in and evaluated the equilibrium line here, you go back into your capital K, you plug in those numbers, that equilibrium, so like this number, the product, I don't have this written in red right now. We would plug in this number here, plug in this number here, and plug in this number here, and get a value for K. Now this should be done 4 times for each of the 4 solutions that you ran in this lab experiment. And these K values should all be very similar to each other. They're not going to be identical, but they should be similar values. I hope this helps. Thank you.